Let's talk about the deep structure of the universe, the architecture of physical law itself. And I'm going to bet it's not what you think it is. You know, when you think about physics, you probably picture things moving around, right? Planets in orbit, apples falling, particles smashing into each other. But what if I told you the deepest, most fundamental idea in all of physics isn't about what changes, but about what stays exactly the same? It's really about a hunt for symmetry, for truths that are absolute no matter who you are or where you're standing. So, what do we actually mean by symmetry when we're talking about a law of nature? Well, to get a handle on that, we need a really solid definition. And the great physicist Hermann Weyl gave us this one, and it's just beautiful in its simplicity. If you can do something to an object, turn it, move it, whatever, and it looks completely identical when you're done, then it's symmetrical. Simple as that. Now, this idea goes way beyond just pretty objects. I mean, sure, a vase is symmetrical if you can spin it 180 degrees and it looks the same, but think bigger. If you build a complicated machine right here, and then you build an absolutely identical one 1,000 miles away, it should work in exactly the same way. That's because the laws of physics themselves have this symmetry. But wait a minute, let's push on this idea. What happens if we take a pendulum clock and just turn it on its side? It stops working, right? So what gives? Do we just break the whole idea? Does this mean the laws of physics are not symmetrical when you rotate things? Turns out the law isn't broken at all. Our definition of the system was just too small. See, it's not enough to just rotate the clock. You have to rotate everything that's acting on the clock. And in this case, that means rotating the Earth and its gravity right along with it. If we could do that, the clock would tick along just fine. The symmetry holds true. Okay, so this brings us to a really central challenge. If the laws of physics are supposed to be universal, they have to work for everybody, everywhere. But what happens when two different people watch the exact same event from two different spots? To figure this out, let's meet Joe and Mo. All right, so here's the setup. Joe sees a particle, and from his perspective, it's at position X. Now, Mo is standing just a little bit away, we'll call that distance A, and he's looking at the exact same particle. But because his starting point is different, he writes down a different number, X prime. They're seeing the same reality, but their notebooks have different numbers. So the big question is, do Newton's laws still work for Mo? So how do we check? Well, the math shows us something kind of magical. Since Mo's position is just shifted by a fixed amount, A, when we look at velocity and then acceleration, which are all about how things change over time, that little a just disappears from the equation. It vanishes. They end up measuring the exact same acceleration. And since F equals m times a, Newton's law works perfectly for both of them. This is called translational invariance. The laws just don't care where you put your 0 point. Okay, that was easy enough. But what if Mo doesn't just slide over, but rotates his entire point of view? Whoa. Now the math gets, well, it gets really messy. All of a sudden, you've got sines and cosines everywhere just to figure out the new coordinates, and then you have to do the same complicated stuff for all the forces. It's a huge pain. But right in the middle of all that trigonometric chaos, physicists noticed something incredible, something they called a crucial accident. It turns out the mathematical rules you use to transform the particle's coordinates are exactly the same as the rules you use to transform the forces. That is not a coincidence. That's a deep, deep clue about how reality is put together. So here's the bottom line. Whether you shift your viewpoint or you rotate it, Newton's laws hold up. They still work. But my God, proving it for every possible angle and every possible law would be an absolute nightmare of calculations. There has to be a better way, a better language to even talk about this stuff. And that's exactly what happened. To solve this whole problem of perspective, physicists didn't just find a new equation. They invented an entirely new language for reality. And this is the hero of our story, the vector. A vector isn't just a list of 3 numbers for x, y, and z. It is the physical thing. Think of it like an arrow floating in space, a push, a step, a velocity. That arrow is real. It exists completely independent of whatever grid lines we decide to draw behind it. The vector is the reality. The coordinates are just one way of describing it. And this is the magic of that idea. Instead of 3 separate clunky equations for x, y, and z, we can write one single, beautiful equation, F equals m times a, where F and a are vectors. The symmetry that we were fighting to prove with all that messy math is now baked right into the grammar of the equation.
If a law is written in vector form, it is guaranteed to be true for everyone, no matter how they're oriented. It's just built in.
So, by using this language of vectors, we can write laws that are true for everybody. But it gets even cooler than that. This language lets us find quantities that aren't just seen the same way, but are pure absolute numbers that everyone in the entire universe has to agree on.
We call these absolute truths scalars. A scalar is just a number. It has no direction. Think about temperature, right? Temperature doesn't have an x component. It's just a value. Joe and Mo will always agree on the temperature no matter how they're standing. That's the ultimate prize, a real, unchanging, absolute truth.
Let me break it down like this. A vector, like velocity, has two parts: a magnitude, which is your speed, and a direction, which is where you're going. A scalar, like speed, is only the magnitude part. The real beauty here is that this new language gives us a tool to distill that absolute scalar truth out of all the messy directional vector information. And that tool, that mathematical magic trick, is called the scalar product, or more commonly, the dot product. It's a special way of multiplying two vectors together that basically cancels out all the directional weirdness and leaves you with one perfect, shiny scalar number that everyone, everywhere, will agree on. And this isn't just some abstract math game. I mean, some of the most fundamental ideas in physics, like kinetic energy and work, are scalars that you calculate using this dot product. Energy has no direction, and that's because it's the absolute scalar result you get when you combine vector quantities like force and displacement. This math is actually uncovering the deep structure of reality. So let's bring it all home. Physical reality could not care less about the coordinate systems we draw on paper. Vectors weren't just a clever shortcut. They were invented specifically to build Hermann Weyl's original definition of symmetry, that idea of invariance, directly into the very grammar of physics. If you use vectors, your laws are guaranteed to be absolute. And that leaves us with a pretty mind-bending final thought. We just saw how inventing a new language, the language of vectors, didn't just make our equations prettier. It revealed a hidden, deeper, more elegant truth about how the universe works. So it really makes you wonder, doesn't it? What other profound secrets about reality are just sitting there, completely invisible to us, simply because we haven't yet invented the right words to see them?